couple of different approaches that we could look at. One is called a periodic rebalance, and frankly, this one is pretty crude, right? This is not fancy. It's a little bit more crude than we'd like, but if you just need some way to make it happen once in a while, and when I say once in a while, you might think of the fact that maybe before you write the thing to disk, because maybe tomorrow you're going to load it back up into memory, maybe before you write it to disk, you do the periodic rebalance, you write it to the disk, so tomorrow when you read it back, it's all fresh and height balanced. That would be the kind of periodic thing. Or once an hour, you run code that kind of cleans it up and just makes sure that it's good, right? But it is a little crude, and it's going to take a little bit of time, etc. But certainly this is a way that we can understand. So here's how we can do it in that crude fashion. First, walk the tree, right? Walk the tree and make a sorted array. So in our case, regardless of how this goes, let's just pick some numbers, and let's say that we walk the tree, and let's get the numbers in order 26, 31. Okay, so let's say that we ended up with that tree, and or that array made from this, and let's write index numbers here just for our own reference, 4, 5, 6. So do an in-order traversal and walk the tree, right? By doing that in-order traversal, make an array out of all of that data. Then split it in half, right? So find the middle, in other words, right? So the middle is going to be, in this case, 0, position 0 plus position 6 equals 6 divided by 2. That's going to be position 3, right? So the middle that we found is position 3. Notice that I'm doing here an integer divide. So if it's odd, if it's an odd number of items or an even number, it's going to work okay, right? You can still do this piece. So we find that midpoint, and then we know that that is going to be the next thing that needs to be added. Now we're just going to make a new tree, right? We're going to make a completely new tree, and then we're going to repoint root to it when we get done here. So that then gets tossed into the new tree with just a normal add operation, and we know it's going to become the root. And then you're going to recurse to the left. So what is that going to mean? Well, now our boundaries are going to be 0 to 2, whereas here the boundary was 0 to 6, right? That's the array. But now, since we're recursing to the left, we're only working with these three, right? These three items. So again, here we take the middle. The middle is going to be 0 plus 2 equals 2 divided by 2 equals 1, right? So now this is going to be our midpoint. So now that one goes, that's the 4 is going into the array, whereas here it was the 19 that went into the tree, sorry, right? So the 19 got tossed in the tree here. In this case, it's position 1, which contains the 4, that goes into the tree. So we're going to keep doing that, recursing to the left and recursing to the right, because once we're done with that one, then we got to come back and think about these, right? So if you keep doing that, recurse to the left, recurse to the right, you're going to figure out a new tree that is going to be exactly height balanced, okay? So if we were to go and write this out and follow that whole thing, it doesn't mean that you have the same number of nodes on both sides, and it doesn't mean that it's always the same height left and right, because sometimes the number of nodes won't allow that to be true, but it will always be height balanced, which, remember, is that the number of nodes is off by no more than 1. Not the number of nodes, sorry, I said it wrong. That the height of the left tree and the right tree are off by no more than 1. And this will guarantee that you get that, because as you see, right, this is going to be balanced because this is a middle number. So we know if that's the root, you're probably going to be okay no matter how it falls in the end. Okay, does that make sense? So it takes walking the tree, which is going to be which is going to be big O of n. That's right. You're starting by making an array out of the tree, right? Doing an in-order traversal and copying the items as you reach them into a brand newly created array, right? Then you're doing this recursive method algorithm where you pick the middle, throw it into the tree, then recurse to the left and then recurse to the right, and keep doing that all the way until you get lists of one, and then you know you're done, and then you're going to have a balanced tree when you recreate that thing. Then you discard the old tree and point root to the new one. Actually, you can discard the tree before because you've put them in an array, right? So you can actually toss the tree away and just use the same root and just call add as you throw these things in there. Does that make sense? Okay, what questions do you have about this idea? It ain't pretty, right? It ain't pretty, but it'll work. You have to do the